Alright, what's up, guys? This is our project presented by me, Bhavi, and Jonah,
Hello.
and we are going to solve a calculus problem today. Alright, so our problem that we're going to be doing is going to be related to the gold rush. So consider the production of gold during the California gold rush from 1848 to 1888. The production of gold can be modeled by this equation right here, where where t is the number of years since the rush began. So t ranges from 0 to 40, where 0 years is 1848 and 40 years is 1888. And G is the ounces of gold produced in millions. So a summary of the data is shown in the following figure. This is our gold production related to time. So what we need to do is we need to find the maximum, both the local and absolute gold production, when it occurred, and the amount of gold produced during that maximum. We also need to find the minimum, local and absolute gold production, and what the amount was. So our approach into solving this problem is that we're going to take the first derivative of our function with respect to time. So why are we going to take the first derivative? Well, if you recall, the first derivative gives us the slope or tangent line to any point on the function. Now, if you look at this little graph, for an example, we have our small tangent lines at various points. And points where the slope is 0 or tangent line is completely horizontal are called critical points. So you could take this second tangent line, for example, that looks like a completely horizontal line that we could probably consider a critical point. But we will make sure of that. Critical points are points where the graph has either stopped increasing or decreasing and may change direction. To determine whether it's a maxima or minimum, we must consider the slope before and after the critical point, as long as it's within the interval that we're looking at. And to find the absolute maximum minimum, we must also consider the endpoints. To find the critical points of our function, we will take the derivative and we're going to equate it to 0. So now that we have the motivation behind taking the derivative, let's get into it. So we start off with our function, and if you remember from Calc 1, you could probably tell this is a nice little quotient rule. So our top function, we'll call it f of t, so f prime of t will be 25. And our bottom function, we'll call it small g of t, and small g prime of t is going to be 2t. So when we take the derivative, we get this messy looking function, but fortunately for us, we only care about the numerator because that's what's going to make it equal to 0. So once we take the numerator, we get this simplified version, negative 25t squared plus 400 equals 0. We're going to add 25t squared to both sides, and we're going to divide both sides by 25, and we get t squared equals 16. If we square root both sides, we get t equals plus or minus 4. And if you're attentive, you'll notice that negative 4 is not even on our interval, so we're just going to throw it out, and we get t equals 4. All right, I'm going to hand it over to Jonah now.
Hello. So finding our local max or min. So like he said, we use the derivative of the function, set it equal to 0, where we get our critical points are plus or minus 4. But since our domain is positive up until 40, we get our critical point is equal to 4. So when we evaluate the derivative at some point after the critical point, for example, g prime of 3, we get 0.28, and g prime of 5 is equal to negative 0.1338. We can see that the point is a local maximum since the function is increasing before the point and decreasing afterwards. After plugging into the original equation, we get g of 4 is equal to 3.125. Therefore, the local maximum is at the point 4, 3.125. For the domain between 0 and positive 40, for our values, we get for our t value of 0, we get g of t is equal to 0, which is our endpoint and our absolute minimum. For t is equal to 4, we get g of t is equal to 3.125, which are our local max and absolute maximum. For t is equal to 40, we get 0.6188, which is our endpoint and is neither a local max or min. So from the results of this, we get both absolute maximum and local maximum gold production occurred in the year 4, or 1852. No local minimum gold production occurred, but the absolute minimum was in year 0, or 1848. We can see that our results match the predictions we made from the graph in the beginning, where we could see that 1848 is our smallest, and then 1852 is our highest production. Thank you for listening to our presentation and our project.